Welcome, welcome. On behalf of my colleagues at the National Science Foundation and the Department of Energy's Office of Science, I welcome everybody here and all those streaming online. This day marks a very special occasion, revealing and celebrating the first look at the universe through the eyes of NSF DOE Vera C. Rubin Observatory.
Well, thank you, Ed, and thank you to all of you for being here today. Starting today, our ability to understand dark matter, dark energy, and planetary defense will grow even faster than ever before. This exciting new future is thanks to the vision, work, and support of the many people we're proud to recognize here today. Let me begin by thanking the White House Office of Science and Technology Policy Director, Michael Kratsios, and the administration for their continued support of exploratory science. By working across federal agencies, OSTP, NSF, DOE, we turned shared investment and coordination into a transformative interagency public-private partnership. The flagship observatory has been more than 20 years in the making, with NSF behind the project every step. NSF brought together a coalition of partners to build and support the cutting-edge facility, instrument, and data management systems. More than 40 international organizations contributed to building Survey Telescope with the ability to gather more data than all other ground and space-based optical telescopes in history combined. NSF is proud to continue to lead Rubin's operations as it begins to deliver on its promise to expand our understanding of the universe. Thank you to DOE, our international partners in Chile, private donors like Charles Simoni, the National Academies for prioritizing Rubin in the 2010 Astronomy and Astrophysics Decadal Survey, and the entire Rubin team, especially Tony Tyson, Rubin LSST chief scientist who conceived and championed this project from the start. Vera Rubin is the namesake of this facility because she is the symbol of scientific excellence. Her legacy reshaped astrophysics and our understanding of dark matter. Generations of researchers have been and will continue to be inspired by her. Alan Rubin, one of Vera's children who's joining us here virtually today, once told NSF, Vera believed there is always more to be discovered. So let's keep discovering together and proving her right. Now I hand it off to Kathy Turner from the Department of Energy. Thank you.
Hello, everybody. We're incredibly thrilled to be here today for the unveiling of these new images from the groundbreaking NSF DOE Vera C. Rubin Observatory. Just a preview of the data to come. I'm Kathy Turner, Program Manager for Rubin Observatory from the Department of Energy Office of Science. Carrying out this project in partnership with NSF and the private and international partners has enabled us to bring all of our strengths to this amazing observatory. I am honored to work with all of them and look forward to our continued partnership. This observatory represents a giant leap in our ability to explore the cosmos and unwrap the mysteries of the universe. Of great interest also to the observatory's namesake, Dr. Rubin. Now I'd like to introduce Harriet Kung, our acting director of the Office of Science at Department of Energy. With decades of experience in scientific leadership, her vision and dedication have been instrumental in making this amazing observatory a reality. Please welcome Dr. Kung.
Good morning, everyone. Thank you, Kathy, for the wonderful introduction. On behalf of the US Department of Energy, let me add my thanks to the long list of organizations that has made today's event possible. First of all, national academies. I would especially like to single out the Board on Physics and Astronomy and also the Space Studies Board for hosting us in this beautiful auditorium today. I also want to thank White House OSTP, the National Science Foundation, and also the Association of Universities for Research in Astronomy, as well as my colleagues in DOE's Office of Science, for putting together the wonderful program that we will witness today. But let me first introduce a short video from the Secretary of Energy, Chris Wright, who is not able to join us today, but he took the time during his recent visit to SLAC National Accelerator Laboratory to film the video you'll be seeing shortly. So let's cue the video.
Today we celebrate the culmination of 2 decades of scientific and technological innovation that have given us an ability to look into the cosmos, to understand our universe itself. This is the Vera Rubin telescope in Chile, and I want to congratulate all of those at the Department of Energy and the National Science Foundation, those working at SLAC out here in California, where I'm standing right now, and those on the ground in Chile, for this tremendous technological achievement that truly will bring an understanding of our universe simply not possible before. The movie has started, the camera is running, and we're going to see our cosmos unfold before us. Congrats to all.
Thank you, Secretary Wright. Having this event today really feels like a homecoming. It was really the 2010 National Academy Decadal Study for Astronomy and Astrophysics that recommended that our high-energy physics program partner with NSF on what would become the Rubin Observatory, which was the number one top-ranked ground-based project. As Brian has already mentioned, the NSF DOE Vera C Rubin Observatory was a project long in the making with many moving parts. The DOE's Office of Science was proud to lead the construction of the LSST cam, the largest digital camera ever built. It is the size of a small car, but twice as heavy. The camera, boasting an impressive 3,200 megapixel resolution, was lovingly designed and fabricated by scientists and engineers at SLAC National Accelerator Laboratory, with critical contributions from DOE other national laboratories, as well as international partners. This camera, in conjunction with the Simone Survey Telescope, will create a 10-year survey of the sky in the Southern Hemisphere, known as the Legacy Surveys of Space and Time. This treasure trove of data set will give researchers unprecedented depth and clarity to questions that drive the fundamental research supported by DOE's Office of Science. And some of the questions include, how can we better understand the matter and energy that makes up 95% of our universe? And why is our universe ever expanding quickly, and how is that pattern change over time? And also, what role did dark matter play in how our universe evolved? We anticipate that the observatory will give us many insights into our past, our future, and possibly the fate of the universe. Answering these questions is a challenge that is matched with the many, many talents that contributed to today's success in the survey. And we at DOE are extremely proud of the many people that have contributed to this amazing project. We're especially grateful for the indispensable cooperations from our international partners. In particular, the success of the Rubin Observatory relies on its location high atop Cerro Pachón in northern central Chile. That's why I'm so pleased to introduce to you His Excellency, the Ambassador of Chile to the United States. Ambassador Juan Gabriel Valdez has dedicated his career to fostering strong ties between our nations. Please join me in welcoming Ambassador Valdez. Thank you.
Good morning, everyone. Mr. Michael Kratsios, Director of the White House Office of Science and Technology Policy. Mrs. Harriet Kang, Acting Director of the Office of Science at the Department of Energy. Mr. Brian Stone, performing the duties of the Director of the National Science Foundation. Distinguished American and international authorities, esteemed scientists and friends of the National Academy of Science who welcome us today. I'm very happy to be here today. I have to say that I have received a number of calls from our friends, astronomers in Chile, saying that I had to be here today. Therefore, it's a fortune to be representing them this morning. Chile is without a doubt an astronomical nation. Evidence of astronomical observation by our earliest inhabitants dates back more than 2,000 years before Christ. Our geography gives us clear, dry, and stable, ideal skies for observing the stars. Astronomy is part of our identity and our heritage, and we are proud of it. But it is not only nature that has led us to become global leaders in astronomical observation. It is also the result of our government decision, a clear and sustained policy of international cooperation, scientific development, and the protection of our dark skies. Today, we celebrate the first images from an extraordinary telescope, the Vera Rubin Observatory, equipped with the largest digital camera ever built for astronomy. But we also honor the memory of an extraordinary woman. Vera Rubin was not only a pioneer who uncovered key evidence of dark matter, she was also an inspiring example of integrity, perseverance, and humanity. Vera Rubin pushed the boundaries of scientific knowledge, but also her era. Naming this observatory after her is a profoundly symbolic and just act. It sends a message to new generations, and especially to the children and young people of Chile and the world, that knowledge has no gender and that the university is open to all. Vera Rubin has been the inspiration for the important and growing number of women astronomers we have in our country. For Chile, the observatories represents our commitment to knowledge, to sustainable development, to international cooperation, and to the defense of dark skies. The Vera Rubin Observatory is part of a unique ecosystem. Today, more than 40% of the world astronomical observation takes place in Chilean soil. And by 2030, that number will exceed 55%. This also places a great responsibility on us to protect our skies, to support science, and ensure that the knowledge generated here benefits all of humanity. Finally, I would like to thank everyone who made this project possible and who placed their trust in Chile as a strategic partner. The institutions of the United States government, especially the Department of Energy and the National Science Foundation, the international consortium led by Aura, the universities, engineers, technicians, and local communities that participate in this process, and to all who dream of uncovering the mysteries of the universe. We are delighted that the United States is looking at the universe from Chile. Thank you very much. I now invite Dr. Harriet Kang, the Acting Director of the Office of Sciences at the Department of Energy, to address us. Thank you very much.
It is now my distinct honor and privilege to introduce Michael Kratsios, Director of the Office White House Office of Science and Technology Policy, and Assistant to the President for Science and Technology. Director Crazio previously served as Chief Technology Officer of the United States during President Trump's first term, where he advised the President on landmark initiatives in artificial intelligence, 5G, quantum computing, and advanced manufacturing. Looking back, many of these initiatives not only had launched, but have continued to shape the trajectory of the nation's science and technology. Today, he continues to advise the President on emerging technologies and helps drive America's leadership in critical sector vital to our national strength. Please join me in welcoming Director Crazios as we mark yet another milestone in America's golden age of science and technological greatness. Welcome, Dr. Crazio.
Good morning to everyone here and watching online. Thank you, Dr. Kung, for that introduction, and thank you all for joining us as we celebrate the completion of a monument to American leadership in fundamental science. The American people have always been animated by a spirit of exploration, and our national story is one of pioneers seeking new horizons and endless frontiers. It is fitting then that with the construction of the NSF DOE Vera C. Rubin Observatory, we will once again see further into space and deeper into time than ever before or anyone else. These first exquisite images made public today remind us of the full meaning of the words like awe and wonder and the limits of our language. They are sublime in their beauty, overwhelming in their scope, and profound in their promise of the discoveries to come. Like the majestic Hagia Sophia, with its soaring golden dome and glowing mosaics, lifting the spirit towards the divine, the Rubin Observatory draws our eyes and our hearts upwards to the heavens. Long before Aristotle demonstrated that the earth was round, and even before Abraham looked up at the stars and saw the promise of God, humanity has peered into the skies in reverence, seeking to understand our place in the cosmos. We believe the work of this observatory will help us find long-sought answers and ask new and better questions. It will also provide the best map mankind has yet made of our region of the universe. From the Lewis and Clark expedition to the Voyager probe and the Hubble launch, America's greatest efforts into the unknown have been public goods supported by the far-sighted leaders in government. Some projects are just too big, too genuinely monumental for any other institution to take on. Only we, the people of the United States, can do it. In its primary mission, executing the legacy survey of space and time, the Rubin Observatory is a joint initiative of the National Science Foundation and the Department of Energy's Office of Science. It represents a whole-of-government effort, a magnificent partnership of the many components of the federal research ecosystem, demonstrating our shared work at its best. Let me extend my thanks to everyone whose efforts have brought us to this day, including Brian Stone, Harriet Kung, and Ambassador Valdez. We know that the best environment for truly groundbreaking basic research is collaborative and interdisciplinary. Thanks especially to the scientists of the National Science Foundation's National Optical Infrared Astronomy Research Laboratory, under the management of the Association of Universities for Research and Astronomy, and DOE's partners at the SLAC National Accelerator Laboratory. Each part of the national research enterprise has their role to play in this truly magnificent work. The telescope at the Rubin Observatory is a triumph of American technological ingenuity and skill. Its 27.5-foot mirror combines the primary and tertiary mirrors into one surface and was manufactured over the course of 7 years at the Richard F. Karras Mirror Lab at the University of Arizona. The 6,000-pound digital camera is the largest ever made, the size of a car, custom built by SLAC, with a 3,200 megapixel CCD array and 9.6 square degree field of view. That means it could take a picture of 45 full moons at a resolution so high it will need a wall of 400 ultra high definition televisions to show it at full size. The 20 terabytes of data produced a day will be transferred to SLAC minute by minute for initial processing and distribution. With its unique mirrors, unrivaled camera, and trailblazing AI computing infrastructure, the observatory represents an investment by all of us in the future. Ours is a country of beginnings, of projects, of designs and expectations, too many of which have been borrowing from posterity for the comfort of the present. The project is, instead of a burden of debt, a gift to our children, one of which will lay down a cornerstone of knowledge and basic research today on which they will proudly build tomorrow. All of our most extraordinary technological advances and increases in our awareness have rested on new paradigms in fundamental science, as our brightest minds have groped closer to the truth of things and uncovered the mysteries of creation. In their knowledge of our ignorance, scientists like Vera C. Rubin have named two of those mysteries, dark matter and dark energy. And we all hope that with the help of the Rubin Observatory, these hidden cosmic neighbors will eventually uncover themselves to human science. In the meantime, I trust that the stunning images and staggering amount of data the observatory will produce will support exceptional scientific efforts around the world. The United States remains at the forefront of international science and technology research efforts, a leader whose partnership is always wanted. More importantly, even more than that, I hope the observatory and its work inspires America's children with awe and wonder at the grandeur of the cosmos and causes them to fall in love with the sciences and mathematics. So congratulations to everyone whose leadership and hard work made today possible. Your nation is proud of you and very proud of this observatory. And thank you all for joining us as we celebrate this achievement. And now, for the reason we are all actually here, let's see some of these amazing images.
You can plan, but sometimes things don't go as planned. We were hoping that Director Kratsios would show you first image. This observatory is the greatest astronomical discovery machine ever built. And we finally started working with it. This is the first image that we are unveiling to the whole world today. Thank you for your reaction. But now that we looked at this image, I have to reveal a fun fact. This image actually shows only a small portion of one Rubin image, just about 2%. In other words, the entire Rubin image is 50 times larger than what we are seeing here on the screen. So you may wonder, why didn't we show the entire image? Let us see why. Rubin Observatory, including its Simony survey telescope in the middle, LSST camera on the left, and an exquisite software framework, is designed to make huge images rapidly. These three components you can see on the screen and their technological breakthroughs is what makes Rubin and LSST possible. Let us first have a quick look at the super agile Simony survey telescope in the middle. You will notice the color scheme is matching everywhere, and indeed, my official Rubin tie is modeled after the telescope. Here you can see Simone Survey Telescope inside the observatory's dome. The point of this short video is to demonstrate the amazing ability and agility of this 300-ton telescope. No other large telescope in the world can move this fast. It moves around in seconds. Other large telescopes take minutes. Let us now look quickly at the LSST camera. This big, beautiful camera is already in the Guinness Book of Records as the largest astronomical camera ever made. It makes huge images. As we just heard, just one Rubin image covers sky area equal to 45 full moons with its 3,200 megapixels. But that many pixels makes it very hard to display such an image. This is more pixels than the human eyes, your eyes, my eyes, can see. And this is the main reason why we could not show you the entire image right away, but only this small image shown in the bottom right. You can see its relative size to the full field of view in this small rectangle at the bottom. As Director Grazios pointed out, we would need 400 high-definition televisions to properly display just one Rubin image so that your eyes could capture all the detail. That means covering a basketball court with 400 TVs to display just one image so that your eyes can see all the detail. But instead of looking at 400 TV screens or walking around the basketball court, our team has developed a powerful web display tool that we can use to move around our giant images. We can zoom in and zoom out. We can explore and admire details of any object you choose to look at. Next, we will look at a region of sky about twice as large as one Rubin image. It is centered on the giant elliptical galaxy called Messier 49. This region that we'll explore in a second is about 100 times as large as the first image we saw today. The follow video is 1 minute long, and we will first enjoy it without any comments. Then we will replay it, and I will comment. Enjoy. We will look at it again. Before we start, I want to say that the entire Rubin team is so excited about this data. We have been talking about this data for over 2 decades. It's finally here. Let's look at it again. Please pause. You can see here a universe teeming with stars and galaxies. The seemingly empty black pockets of space between stars in the night sky, when you look at it with unaided eyes, are transformed here into these glittering tapestries. There is barely a pixel in this image that doesn't have some light coming out. And only Rubin can produce quickly such large images with this much color and richness. Please continue. Play. You can see spiral galaxies, elliptical galaxies, clusters of galaxies. Please pause here. This is an amazing region. We need to stop here. I love it. Do you love it? Okay. Everybody loves it. Here you can see a stunning variety of celestial objects, from bright stars in our galaxy, ranging in colors from blue to red, to these nearby blue spiral galaxies, to more distant elliptical galaxies that are yellow and red in color. You can see how vividly these colors are, and that's very important for science. Colors of galaxies are very important because using these colors, we estimate distances to these galaxies. You can also note in this image that galaxies are not randomly distributed in it, but they are clumped. They show clumping and statistical details of that clumping, and distances to these galaxies determined from LSST colors will enable very precise, unprecedentedly precise studies of the expansion history of the universe and studies of dark matter and dark energy. That's what we measure, where these galaxies are, how big they are, and what are their colors. And in few years, LSST will be producing unprecedented cosmological results. Let's continue. And now you can see the full extent of that image. It's about 2 LSST or Rubin fields of view. And this is how we scan the sky, 30 seconds per exposure. There were about 10 million galaxies, close to 10 million in that image. Thank you. This slide shows again the whole area that we just looked at the end of video, with the first image from today outlined in the top left corner, that small portion where your eyes could tell the detail. Known objects here are annotated with their names, and you may notice that most faint objects do not have their names shown, and that's because they have not been studied before. Most of these objects have never been seen by people before. As we already discussed it, in this projection, you simply cannot see all the details in this image because our human eyes and our screens are not good enough and large enough. There is so much more in this image that you can enjoy, that you could see in that 1-minute video. And you can actually do it yourself later at home using our tool that we developed for this purpose. All you need is internet, and at the end of the presentation, I'll give you a QR code with a link. And now I'm talking to our colleagues and friends on the internet watching us through YouTube. At the end of the presentation, you will get a link, and then you can spend the rest of your day enjoying these 10 million galaxies. We hope you enjoyed it, but there is more to show you today, much more. Imagine now an image like what we just looked at, but imagine it 1,000 times larger. That would be half of the sky, or the entire sky visible from Chile. That 1,000 times larger image than this giant image we just looked at, this is LSST, Rubin's main goal for the next 10 years. But LSST will be so much more than just an image, even though such great large image, it will be so much more than just an image. And that is because every object included in LSST, about 40 billion of them, for the first time more celestial objects than living people on Earth. Every object will be imaged about 800 times during these 10 years that it will take to deliver LSST. And that brings us to the greatest movie of all time, LSST. Because we will have 800 different observations, we can take these frames, we can put them in a movie, a digital color movie of the night sky. As I said, Rubin Observatory is the greatest astronomical discovery machine ever built. So let's see quickly what makes it so uniquely powerful. Most importantly, it can scan the sky super fast, about 10 to 100 times faster than any other large telescope. This is like comparing the speed of your car to the speed of an airplane. That's what we are doing. Instead of driving around from east to west coast for many days, we pop on a plane and we are there in 5 hours. That's what we are introducing here. It took us a few nights to collect data we are showcasing today. With existing facilities before Rubin, it would have taken at least a year and maybe more. And LSST would take 1,000 years, which is obviously impractical, not 10 years. This is why we had to build Rubin Observatory. And so let's talk now a little bit about movies. We have a couple of trailers to show you. So objects, we make movies of the night sky to see two things, objects that move and objects that change brightness. So objects that move come in two flavors. Stars in our galaxy move, and they move slow. We detect it, but it's slow. Much faster objects are asteroids, and they are in our solar system. And so we'll focus now on asteroids that we discovered in those few nights of data. So here, nothing is moving yet. This is just to show you a tiny portion of that image that we will zoom in to discuss asteroids. Nothing is moving here either. What you can see is two spiral galaxies. What you cannot see is that these two beautiful galaxies were photobombed by asteroids. Let us see how. Here you can see asteroids as colored streaks. They are not satellites. They are asteroids that move during exposure. And this color image is made by combining many individual exposures. But asteroids, because they move, they disappear after you got one picture of them, one exposure. So these colors correspond to the principal colors used to construct color image. So you have red, you have green, you have blue. And so these asteroids, when we combine the image, we can remove them. Our software is smart enough to recognize them and remove the streaks when combining individual images. This is why you did not see them before. But now we will focus on asteroids. It's another 1-minute video. It showcases our unprecedented ability to detect small objects orbiting the sun. You can see motion against the static background of stars and galaxies. And we are only showing asteroids discovered by Rubin, not previously known asteroids. These are all new discoveries that were reported to the Minor Planet Center at Harvard this morning. There are so many of them. Just a few nights of data, just one tiny region on the sky. And now you will see their location in solar system. Let's pause here. So this blue donut, this is simulation of all the asteroids we expect there. And because we only spent few nights to get these data and we looked towards one small region on the sky, all of these new discoveries are found in this one narrow slice of this big donut. In 2 or 3 years, after we start LSST later this year, we will sweep around and discover all of these millions of asteroids. So we had 2,000 in these few nights of data. There are 7 near-Earth objects that have orbits that cross Earth's orbit. None of them is in such position to strike Earth, don't worry. We'll get tens of thousands more near-Earth objects. And we will discover about 5 million new asteroids during the next few years with LSST. This is 5 times more than all the astronomers in the world discovered during last 200 years since the discovery of the first asteroid. So because of this rapid development of technology today, we can outdo all these 2 centuries of effort in just a couple of years. Let us now see another illustration of the ever-changing night sky. We will look at objects that change their brightness. They don't move, but they change the way they look. We will look at stars that are called variable stars because they vary in brightness. They can change brightness on time scales from minutes to years. And by the end of LSST, we'll have data, we will know of about few 100 million variable stars. This is mind-boggling to people who work in this field. LSST will also discover a few million supernovae. Supernovae are exploding, dying stars that are very important for cosmology because it's relatively easy to estimate their distance. We will now take a detailed look at a few variable stars called RR Lyrae. They can become twice as bright in only a few minutes, half an hour. That's why we chose them for this presentation. They are in reality about 50 times more luminous than our sun. And they change brightness because the whole star is pulsating like this on time scale of some hours. They are also very useful for studying dark matter in our galaxy because we can get their distances easily too. Here you see this blue star. It's blue because it's hotter than our sun. Our sun would look yellow in this image. And here we are comparing its brightness. Please pause here. So what you can see is color image of that star, average color image, and these 2 observations show its brightness in individual images. And the one in the middle is 30% brighter than the one on your right. It is hard to tell with your eyes, but it is very easily measurable in our high-quality images with our high-quality software that goes through those images. Let's continue. We'll see a few more RR Lyrae. The next example is even harder to tell with your eyes. It's only 11%. But again, for our powerful, precise software that looks at it, we know it's 11% and not 10 or 12. All these stars are found in our home galaxy, the Milky Way. It's easy to get their distance to distances much further than we can do today. And so over the next few years, we will map the distribution in the outskirts of our galaxy of both stars and dark matter more precisely than ever before. As you can see, the strength of Rubin and LSST is in huge images, in fast scanning of night sky, in discovery of huge samples of billions of celestial sources, and in studies of those sources with time, how they vary with time. Do they move? Do they change brightness? And that is the real purpose why we built Rubin Observatory. But there is one more thing to tell you today. As we look at the sky, we don't only collect huge samples, we make images of beautiful objects. And so today we want to share with you few beautiful objects, and we chose the Trifid and Lagoon nebulae. These nebulae are giant clouds of gas and dust, and they represent stellar nurseries. They are places in our galaxy where new baby stars are born by those clouds collapsing and becoming hotter and denser until you end up with a protostar, with a young star in the center. So this is the whole image. There are 2 nebulae. Top right is the Trifid Nebula. This pink nebula in the bottom is called the Lagoon Nebula. Again, this image is very large. It's about as large as the entire Rubin image. And your eyes and our screen are not good enough to display all the detail that we recorded in that region. Again, we will show through video that zooms in around all the vivid detail that is captured in that image. So, ready? Warp 1, engage. Wrong video. How did that happen? Peculiar. Huh. All right. We will have to leave that for later. So let me say a few words about what's next for us. That video, by the way, you can see when you follow the link from before, so nothing much is lost. You can enjoy it later. So we've just seen mesmerizing treasure trove of the stuff that LSST will start producing. We are getting to the close of the construction project. We are not done yet. We have some commissioning work to complete, some verification work to complete, but in a few months, we expect the project to be completed. We go into operations, and we will start this greatest digital movie of the night sky later this year, and it will go for 10 years. We did not talk today much about science, but I do want to mention over 2,000 LSST scientists who are eagerly awaiting the start of LSST survey. We want to thank them today, thank them for helping us to arrive to this point with their support and expertise. They helped us first build the science case for LSST that led to LSST being ranked #1 in NAS Decadal Survey in 2010, and they also are helping us to build Rubin Observatory. They are organized in 8 topical science collaborations, and they greatly benefit from the supporting nonprofit organization called LSST Discovery Alliance. It's formerly known as LSST Corporation, and that is the organization that started this project. But I also want to emphasize it is not just the scientists who will enjoy LSST data. It is everyone with curious mind interested in what's up there. Every child in school, we will have tools and materials that our education and public outreach team produced that you can use to be citizen scientists, that you can see in videos in planetaria, that if you're a teacher in high schools, it maps on your science curriculum. All of these will be available from that link QR code in this slide. And so now I will finally finish this brief presentation. The entire Rubin team, and let me add that I was greatly honored by our Rubin team to represent us today. The entire Rubin team hopes that you enjoyed this presentation. Please stay tuned for the exciting discoveries expected from LSST over the next 10 years and beyond. Thank you all here. Thank you all who are watching us over internet. Hundreds of locations in the US and Chile. Thank you and muchas gracias. Thank you to several hundred, close to 300 other locations around the globe. Hvala svima. And thank you for being with us today. And a big thank you to SLAC and Aura, our managing organizations. Heartfelt thank to our funding agencies, NSF and DOE, to our awesome program officers, Dr. Eda Jar, Dr. Kathy Turner, thank you, thank you, thank you. And finally, we are all very grateful to our host today, the US National Academies of Science. Thank you for having us. Greetings to all from the Rubin team. Thank you. This is for the Rubin team. Thank you, Rub. Thank you. We will now continue with our press conference. We will have a panel of Rubin experts that will be answering questions from our media representatives. So I would like our panel to come and join me on the stage, and then we will introduce them once they sit down. Okay, while you are getting on the stage, let's play this beautiful video. We start in the Trifid Nebula. We zoom out. You can see this. Now you can see the background composed of hundreds of thousands of stars. You can see beautiful colors that are due to light from stars bouncing off different types of gas, hydrogen, helium, and oxygen. You can see these dark spots. They are not holes in the sky. They are dark clouds that absorb light between stars behind them and us. They are in the middle. These are not holes in the sky. Here you can see a cluster of baby stars surrounded by this pink emission. These are all new stars that were born in the center. Again, more beautiful dust clouds. There are stars, just as many as outside the clouds, but that cloud blocks the light. And again, such a large image with so much detail, such vivid colors, to produce it in a reasonable amount of time, you really need Rubin Observatory. So if we could go to the last slide. Actually, I think I remember names of all of my colleagues. So let me start with Sandrine Thomas.
Afternoon, good evening, everyone, wherever you are. My name is Sandrine Thomas. I'm the Rubin Deputy Director and Telescope Scientist. And for the last 10 years, I've been honored to work with a very talented multinational team focusing on delivering the sharpest image quality that was possible and enabling the telescope to scan the entire southern sky in only a few nights with this exquisite image quality.
Thank you, Sandrine. Aaron Rudman.
Hello, I'm Aaron Rudman. I'm a professor at the SLAC National Accelerator Lab at Stanford University, and I've been honored to lead the team at SLAC that built the world's largest camera. I'm particularly excited about the discoveries that the Rubin Observatory will make, and particularly eagerly awaiting the light that we will shed on the nature of dark energy and dark matter.
Thank you. Victor Krabendam.
Good morning. My name is Victor Krabendam. I am the project manager for Rubin Observatory. I joined the project 21 years ago, but it's been my honor for the last 13 to be leading the project. The team that we represent here today is an incredible one. We have persevered, we've innovated, and we have overcome challenges. And right now, we envisioned that the project was going to be everything that we dreamed it would be. I look forward to delivering this project on budget and handing it over to the operations team later this calendar year. On behalf of all of the scientists, the engineers, the administrators, and the technicians, I want to thank both agencies and some early donors for trusting us with over $800 million to make this ambitious project a reality. Željko mentioned Dr. Turner and Dr. Ajar. I just want to recognize the teams of people at both agencies that have supported and worked with us with this invaluable stewardship. The first look data that we have seen today is to be celebrated by everybody that has participated in some way in this project, and to all of the people that supported us for the last 2 decades. And we thank you all.
Thank you, Victor. Steven Ritz.
Hi, everyone. My name is Steve Ritz. I'm a professor of physics at the University of California in Santa Cruz and a member of the Santa Cruz Institute for Particle Physics, SCIP. I am the project scientist for Rubin Observatory construction. And in addition, I've had the great privilege of leading the group that was responsible for producing all the images and image products you saw. And in addition, many of the other image products we didn't have time to show you that are also on rubinobservatory.org now. And I hope you'll check that out. Several members of that group are here, and I'm sure we'll be happy to speak with you, and many of them are online, and the work really represents, as Victor said, the work of thousands of people. Thank you very much. Look forward to talking with you.
Federica Bianco.
Hello, everybody. My name is Federica Bianco. I'm a professor of physics and astronomy and public policy and administration at the University of Delaware. I'm a resident faculty of our Data Science Institute, and I'm deputy project scientist for Rubin Observatory. And in that role, I lead a committee that is figuring out exactly how we're going to take this cosmic movie. Where are we going to point the telescope next? With which color we're going to observe to get the most science out of LSST. And we're doing that by soliciting, gathering, and assembling the input of thousands of scientists all around the world. And the thing that I'm most excited about is how LSST will bring the night sky to life, how it will help us observe and understand phenomena and objects that change on timescales from days to months to years. And I'm sure that in that treasure trove, we will find something that we haven't seen before.
Thanks, Fed. And Claire Higgs.
Hello, my name is Claire Higgs, and I am the astronomer on Rubin's Education and Public Outreach team. Our team works really hard to make ways for the public and everybody to enjoy and appreciate Rubin's data, and I'm absolutely thrilled to be here today to help show some of these images and our first products to you. And so today I'm excited to share what we've got here, as well as other ways we can enjoy through sound, our Skyviewer app to explore that image on your own, and also looking forward to citizen science in the future and so much more.
Thank you, Claire. Mike, we can start now.
All right, thank you, Zelko. So now we'll begin the media Q&A portion. Please raise your hand if you have a question. You can ask one question and one follow-up, and please state your name and media outlets before you ask your question.
Thank you. Issam Ahmed with Agence France Presse. Just a basic question, if you could explain the colors that we're seeing and how they are devised. You mentioned it's based on the heat, and are the colors sort of what a human would see if they were in space, or what do they really mean? And the follow-up is about, obviously we talk a lot about dark matter, dark energy. Will Rubin help us understand that better, given that we're seeing things visually, we're not seeing dark matter? And sorry, I have the third. Why are you wearing green? What's the color choice? The green. Thank you.
So there were two questions, one about the meaning of colors in our images. I think Fed can take this one, and then how exactly we will shed light on dark matter and dark energy. I think Aaron can go with this one. So let's start with Fed.
Sure. So our images are in color. If you were to look into space, when you look through a telescope, when you look just up, you actually don't see stars and galaxies in color. Those color represents wavelength ranges, just like the colors that we see with our eyes, but they're different wavelength ranges than the ones that we see with our eyes, because the telescope sees a broader range of wavelengths so that we can study objects more comprehensively. Generally speaking, we always map a bluer color to hotter temperatures, so it would be bluer with our eyes, but way, way more than our blue, and redder colors to warmer things, all the way down to the infrared or near infrared, which LSST does see.
Thank you, Fed. Aaron?
So Rubin Observatory will be able to study dark energy and dark matter in many different ways. So the unique capabilities of the observatory, especially to see so much of the sky, so many galaxies, so many stars, and to do it many, many times over 10 years, will enable us to assemble a large sample of supernova. Those are exploding stars in distant galaxies. That's how dark energy was, and the accelerated expansion was first discovered. We will see roughly 1 million of all kinds of supernovas and tens of thousands of the kind that are most useful to study the expansion of the universe. By observing up to 20 billion galaxies, we'll be able to study how light from those distant galaxies has come to us. And almost every galaxy has its light bent by the gravitational interaction of dark matter that pervades the universe. That will let us study the expansion of the universe in multiple ways. And by studying the expansion with greater accuracy and precision, that will, we hope, uncover more about the nature of dark energy.
Thank you, Aaron.
Okay, next question.
Hi, my name is Sana Pashankar, and I'm from Bloomberg News. My first question is, how much NSF funding has the project already received, and how much will it need year after year to maintain the research? And then my follow-up will be that, given the proposed budget cuts to NSF in the administration's budget, and the way NSF has already curtailed research funding, can people be confident that the funding will be there needed to maintain the research at the Rubin Observatory?
So we're not going to speculate as to future funding levels or the effect of potential future funding levels. But if you have a question regarding the operations of the telescope and what its mission, we'd be happy to answer that.
What about the first one? Can we talk about the first one, about how much funding they have received from NSF and how much will be needed to maintain observation?
Sure.
Victor.
The NSF has granted the ORA, their steward, for the construction of the Rubin Observatory, $571 million to complete the construction project.
Hi, thanks for doing this. I'm Madison Alder with FedScoop. I have a question about just the massive trove of data this will create and how NSF and DOE have approached making that available to researchers quickly through the science platform and alert system. And then my follow-up would be what the timeline for those tools are going forward.
Steve, do you want to take this one?
I'll take the first part. Thanks for the question. So with all the data, I think you get a sense from Željko's presentation how much data we're talking about. As he said, about 10 to 20 terabytes of data every night. Very early on, people realized instead of sending the data and the software out to scientists, it's much better to bring the scientists to the data. And so there's something called the Rubin Science Platform people work very hard on, where you can actually just log in to the cloud and have access to all of the data, be able to do queries, analysis, and so on. And you know, it just works. It's fantastic. Rather than having to distribute software, you just have it all there set up for you. So that is something that is, you know, I think we're very excited about. The timeline, we have a sequence of data previews from the commissioning data. In fact, the first preview using the ComCam data is about to hit the streets, and then that will be followed by a second data preview from commissioning, and then release of the data through a regular data release schedule that's known to the community.
Can I just add, Željko?
Please do.
And also, so Steve has really outlined how science community can get access to the data, but there's also opportunities for the public, for anyone to participate in this discovery process through citizen science. So our partners as Universe will be hosting citizen science projects that anyone in the world can help us sort through this amazing treasure trove and create those projects. And so, as Steve mentioned, the first data is coming with that was taken with the commissioning camera, and so we'll have our very first small projects coming in the next couple of months that are all kind of building up the foundations and the frameworks and the resources for the launch of the survey and all the projects that will come after that.
Fred, do you want to add a few words?
Yes, let me add on top to that, we also, as you mentioned, we also have the alerts. You've seen how Rubin will build this cosmic movie. We have things we're looking for, we're trying to understand things that change over time. So that particular data product will come through in the form of alerts. So overnight, our data runs really fast from the mountaintop all the way to Slack, where it gets processed. And we look at what changed in the night sky compared to how we know that the sky looks normally. It looked before when we looked at it earlier. And then every time that something changes sufficiently that we can detect it, technically at a 5 sigma level, we package that into an alert packet. So we collect the information about it, where it is, how much the brightness changed, how much the color changed, and we add postage stamps of that part of the image that scientists can use to do their science, of course, but also to trigger other facilities that can take more data about those things so we can learn about them even better. And those get distributed worldwide. That particular data product has no proprietary restriction because we need all of the scientists in the world to point their telescope to learn more about these things that we discover.
Thanks, Fred. Mike, back to you.
Hi,
Hi, Mackenzie Perlman from Science News. And thank you all so much for having this press conference today. Going off something said just a few moments ago, you even talked about the citizen science projects starting, and you've clearly made this all very accessible to the public through your Skyviewer app and other ways. Can you talk about the importance of bringing the public along throughout this journey and over the next 10 years?
Thank you. I'd love to talk about that. So this is an amazing data set, but it's also a very complex data set. And so one of the things that our team that has been part of the observatory since the beginning has been working toward is making many ways for people to engage with this data in whatever form you would like, whether it's just enjoying beautiful images or looking on social media, or we have an educational component, and so we're bringing Rubin data into the classrooms. And one of the things I'm really excited about is the fact that we're about to see a generation of students who can see Rubin data in their classrooms in high school, and then perhaps choose to study that in university, and then go on to maybe make the next amazing discovery that will be in that treasure trove of data that is produced through the survey. And so we have many options like that. One of the other things that's in there is we also have a way to explore the data through sound and sonification. And so that's also part of our Skyviewer app that is just as what you're seeing visually is mapping that color data into a visual landscape. We have a soundscape that also is the same representation of that data that you can explore.
As a reminder, there will be more than one star and more than one galaxy for every living person on Earth. Thank you.
Hi, Sam again from AFP. I have another follow-up on the asteroid detection capabilities. Earlier this year, we had 2024 YL4, a city killer asteroid, which briefly posed a risk to Earth. How will the Rubin Observatory help in these detections? Will we get more lead time? What do you expect to see out of the asteroid hunting and the planetary defense capabilities? Thank you.
I can take that question. So, solar system science is one of the 4 scientific pillars of Rubin. So we have developed software framework that can fully utilize our images to make unprecedented discoveries. We are not particularly designed for near-Earth objects, but because we look at everything, we will be extremely efficient at discovering near-Earth objects. And as soon as we have a plausible discovery, all our data will be on daily basis sent to the Minor Planet Center at Harvard, which is the world's clearinghouse for these observations. And sometimes even within less than 24 hours, everyone in the world will know that there is a potential object that could be hazardous, and they can get more data. In practice, typically, once you get more data, you rule out the level of the danger, but you need more data. Everyone in the world will be able to follow up on Rubin's initial discoveries. Very often, we'll get our own orbits, too. I'm Željko Ivezić, and you can spell it the way I pronounce it.
And your role?
Thank you. I think it's time we gave our journalists online a chance now. All right. So our next question is from James Deenan at New Scientist. What are the unique capabilities of the telescope that enable it to detect so many more asteroids than other instruments? Are these early detections of so many asteroids unexpected, or did we expect this volume of objects? How many Rubin detections will feed into existing planetary defense networks?
They were not surprises. We have exquisite simulations that we used, for example, to predict we'll discover 5 million new asteroids. Can you repeat the first part of the question again? Just the first part.
What are the unique capabilities of the telescope that enable it to?
So that is interesting point. So when you ask for each of our 4 science pillars, which vary a lot, from asteroids in solar system to cosmology to dark energy and dark matter, when you ask what kind of system would you like to have, and we asked that question 20 years ago, you get very similar answers. And that's another power of Rubin Observatory that we didn't emphasize today, that we get one data set that will serve all these different science goals. We do not get specialized data for asteroids, specialized data for dark energy. It's one and the same data set because observatory is designed to be so powerful that we can get such a powerful data set called LSST, which will serve everyone. That's why we can get so many asteroids. The short answer is you need to scan the sky very fast with very large field of view, repeatedly for a long time, and that's what we do for every science program.
All right, thank you. Our next question is from Katarina Miller from the New York Times. She asks that given the length of time it took to bring this project to fruition, how does it feel that the observatory is complete?
I will call on Sandrine.
It's great. It's really an amazing achievement. It's the achievement of, again, I mentioned 10 years of work of a lot of people really carefully and methodically putting everything together, designing properly, using the best technology to align the telescope, to build the camera, and build the data pipeline behind it. It's really the results of a lot of very, very careful and hard work. So that's why it feels great.
Thanks, Sandrine.
So Katarina had a follow-up, and that is, now that the first look milestone is complete, what can we expect next from Rubin Observatory, particularly between now and the start of the survey?
I think that's a question for Victor.
So we are completing the construction project, and what we are looking forward to is finishing up the validation of the observatory and how it functions, tuning it up to make it work exquisitely and continuously. And so for the next 3 or 4 months, that'll be our main objective. And after that, we'll be handing it over to the operations team.
Thanks, Victor.
Great. Our next question is from Megan Bartles of Scientific American. She asked, I know it's challenging given the size of the images, but could a few of you point out something that strikes you as particularly interesting when one of you looks at these images? Essentially, help a non-scientist look at this part of the data the way you do.
So if you look at the image where we had spiral galaxies and you had also clustered galaxies that were more yellowish in color, that tells you how far they are. And when we look at two-dimensional images, all the objects that are different distances, they are projected into one plane. But with the power of this data, the power of recorded information that we decipher with our software pipelines, this projection of 2D image becomes three-dimensional data. We unpack all these objects into three-dimensional distribution. That's what I find exciting about this data. It gives you the third dimension that without this data you just don't get. It's like looking at constellations. Constellations don't have the shapes in reality. These stars are different distances, but they project to us to bears and lions and everything else. Once you have the third dimension, then you realize, oh, that looks totally different. And that's what we want to know with galaxies too, to do cosmology. Aaron.
One thing I would like to add to that is when I look at the images, I often don't pay attention to the beautiful nearby galaxies. I look at the little fuzz balls. And if you zoom in close to any one of our images and in almost any portion of the sky, you will see tiny little galaxies. To the eye, they look like small balls of fuzz. But many of those galaxies are 5 or perhaps even 10 billion light years away and have up to 100 billion stars in them. And those are the galaxies, actually, that we use the most if we want to study the expansion of the universe and dark energy.
Thank you, Aaron. Steve, you want to add a few words?
Yeah, we thought a lot about how to select targets and how to represent images. And I think what we hope as people engage and look at these images, first, I think we hope you see them as beautiful. And they're also a little different from what you're used to seeing, actually significantly different. The difference I would point out, and what we're so excited about, Joko said it, but between objects in most astronomical pictures, it kind of looks like inky black space. That's what you've seen before. But that's not what you saw here. What you saw was that inky black space actually is full of stuff. It's full of galaxies. It's full of all kinds of interesting things. And it's because of Rubin's unique combination of capabilities that we're able to bring that all out and to see it and do the kind of fundamental and broad range of science that Aaron mentioned. And so I hope people just see that and the vast range of colors and vast range of different kinds of objects that we are going to see. In addition, there's all the time domain stuff that you've already heard about. And I think the thing we hope everybody sees also is promise and opportunity to find the new stuff that is just, waiting for us. And so I think it's that combination of things that we're really most excited about. And we hope people will take the time to really explore these images because, as I said, they're different. And it's the reason that the EPO team built the Sky Viewer so that you can have a look around. And we hope people enjoy that.
Thank you, Steve. Mike?
All right, our next question is from Greg Redford, the space reporter at WTOP News here in Washington, D.C. He asks, what is the most anticipated discovery made by LSST? What surprises await?
So there are so many of them, it's hard to pick one. We will be looking for unknown unknowns, but we also know that some of the discoveries will be made. I already mentioned earlier today 5 million asteroids, and not everything will be discovery. We are also doing precise measurements in cosmology, in dark matter, dark energy context. We'll be measuring things precisely. That's one of the goals. We will get some unexpected discoveries, like, for example, interstellar objects that we are now in position to get 10 or 15 of them and get much better understanding than those two that are known, Oumuamua and Borisov. So we will learn a lot. Of course, every survey prior to Rubin and LSST, every big project that scanned the sky discovered many unexpected things. So by that argument, we think we'll discover a lot. But then different people are excited about different things. Maybe Fed can tell us in the time domain context, what are you excited about?
Well, I'm going to double down on the unknown unknowns. And I love the question, because can you tell us what the surprise is? No, it's a surprise. That's a bit tautological. And it's really exciting that it is a surprise. And I want to emphasize how difficult it still is going to be to find those things that we have never seen before. People make the analogy, it's like a needle in a haystack. It's not. It's a needle in a haystack if you don't know what the shape of the needle is, if you don't know what the color of the needle is, if you don't know whether the needle moves through the haystack, and if you don't know really what the haystack is composed of, because there's millions of things in the haystack. We don't know all of them to the same level of detail. So it's really an adventurous horizon. And yeah, I'm very glad that we cannot answer the question what surprises there are going to be, because they're really surprises.
All right, great. Our next question is from Corey Powell from American Scientist. He asked, how will Rubin be able to expand our understanding of the far outer solar system, deeper into the Kuiper belts and searching for interstellar objects, or even Planet 9?
Yes, all of the above. If Planet 9 exists, it is still just theoretical conjecture. If it exists, Rubin is the best positioned observatory to discover it. We will also obtain very sensitive images very quickly over a large area of the sky, including the full ecliptic coverage, the plane in which these objects move. So we will extend the outer reaches of solar system by a large factor. We will see way beyond the orbits where Pluto and other Kuiper belt objects are found. We will be sensitive, it depends on the object size, But we could see Pluto even if it were at 10 times larger distance, roughly speaking. And then for interstellar objects, so far there were 2 discovered, so it is very hard to predict how many we would discover because we don't understand population, it's only 2 objects. But by simple scaling arguments, we do expect 10, maybe 20, somewhere there. So we will be extremely powerful solar system survey.
Thank you. Our next question is from Jenna Ahart from Quanta Magazine. Is there an estimate for how many stars or galaxies are in the first image presented today? How does this compare to the full set of galaxies Rubin will observe?
I think Steve knows all the numbers.
We're still counting, but it's, as Joko said, around 10 million objects. And as Joko also said, we're expecting about 20 billion galaxies and after the 10-year survey, and about 18 billion or so individual stars. That's a lot. When you view them 800 times, that means 32 trillion or 30 trillion observations. Very impressive. And so we're really just getting started. The image you saw of the Virgo field, kind of the impression you'll have for the whole sky after about half the survey, 5 years, just to give you a sense. It's very roughly. And we'll just be able to see objects dimmer and dimmer over time. That's one of the real advantages of continuing to do the survey, to look for new things, but also to measure more precisely Aaron's fuzzy things as well. Does that answer the question?
I think so.
Very good.
Our next question is from Kobe Brown from Astro Kobe's YouTube channel. What are some short-lived or previously unseen phenomena that Rubin Observatory might uncover thanks to its rapid, high-cadence imaging?
Do you want to take this one, Fed?
Again, they're previously unseen and unknown, so no, I cannot answer this question. I can answer that we really do believe we will discover new things.
Can I add? One of the things I like to think about is the fact that when you're talking on a survey where everything's in the scale of billions, these 1 in a million events aren't that rare anymore. You get lots of 1 in a million events if you're talking on the scale of billions.
All right, thank you. Our next question is from Alana Schadwinkel from Der Spiegel. I had a look at the Skyviewer app and wondered, is the idea that anyone can discover something in this image that no astronomer has found yet? If so, how could one know if something is truly new? And what does someone actually need? What kind of knowledge or tools to be able to find something new in these images?
Claire, would you like to comment?
Yeah, so that is one of the things I think is very fun, is if you zoom in and you look at one of the little fuzzy galaxies in there, you might be the first person to be paying attention to that fuzzy blob. Someone might have glanced at it before, but you can choose your favorite in there, which is very cool. If you, using that app, you can find the position, which is given in RA and DEC, which are our coordinates, and you can look at other catalogs online that would, if there's information about that, they'll be in there. But there'll be a lot of things in there for which there is no name, there is no catalog yet until all the amazing science of Rubin comes out.
Steve, would you like to add?
Yeah, let me just add one other. There's so many great things about Skyviewer, but one of the really cool things, if you discover a scene you like or an object you like, you can zoom in to it, frame it how you like, and then the button on the lower left will give you a URL, something you can paste into any browser and share it with your friends, and they will see the same scene. So you can, that's so much better than saying, oh, you know that big elliptical galaxy sort of off to the left, go down a little bit there and then a little bit over, or try to read the RA and DEC, which you can also show or turn on and off. There are lines of constant RA and DEC. It's so much easier just to use this fantastic URL generator, and we're hoping people just, share their favorites.
Thank you, Steve. Mike?
So I think that's all the time we have for questions today. This will be the last question.
Yeah, I just perked up when you talked about Oumuamua. Do you think you'd be able to resolve the question of its origin, if it's artificial or natural, by pointing at it where you think it is now, or we know it is now?
I'm sorry, can you repeat?
Oumuamua, do you think you'll be able to resolve its artificial or natural origin based by pointing at it now?
Oumuamua is long gone. We cannot detect it, but we think we will learn more about that interesting question because we will have a much larger sample. We will get between 10 and 20, maybe even more, and then by studying statistical properties of those objects, we can ask, is it more consistent with some natural population, or we can go to far-fetched theories too.
If it comes back.
Thank you again.
Jelko didn't introduce himself, but he is the director of the Rubin Observatory.
No one answered the question about
Hey.
I know, we didn't answer that
Shout
question.
out to the community. Though.
Yeah.
Should have.
I'm Arul Mozi, representing the National Academy of Sciences. The Vera C Rubin Observatory first look images and discoveries are awe-inspiring. That is sure to inspire current and future scientists for a long time. It is very satisfying to see the recommendation from the National Academy's Astro 2020 Decadal come to fruition by the hard work of the scientists and technologists with federal funding for science. I thank all the speakers and panelists on behalf of the National Academies of Science, Engineering, and Medicine, under whose auspices that the Board on Physics and Astronomy and the Space Studies Board hosted this event. I now invite the audience to the reception in the Great Hall, but I understand we're going to replay the video of the nebulae before that. Thank you all very much.